All right, welcome back. Let's talk about some more about the properties of the normal distribution. All right, since we know that the area under your standard normal distribution, your area under the curve, is equal to 1, there should be some way to figure out what this much of the area is. Okay, the area where x is between or equal to a and b. Okay, so it's between a and b, the area under the curve. Must be some way to calculate that. We're going to be using the empirical rule to give you an approximation. We're not going to be doing calculus. That would give you the exact area under the curve. But let's look at what else we could find out. Okay, this area also. We could look at the area less than or equal to d. By the way, we are talking about all of the values of x, possible values of x for this distribution, and we are interested in those values of x that are less than or equal to d. So there is d indicated by that line, and we're looking at all the area to the left of that. So let's clear this up so we can move on. All right, let's see if we can get this to move around. Okay, but what if the mean or the standard deviation changes? Changes between data sets. What if they have different data sets? Let's take a look at something. Here is the case where we have two different data sets, two different samples, and the mean, well, two different populations, because we're using population symbolism, seen right here and right here. Okay, so two different populations. The mean of the first population is 0. The mean of the second population is 3. But look at the standard deviations. They are exactly the same. So all that happens to these two normal distributions is what they are shifted along that axis from each other. One has a higher mean than the other. So what if the standard deviation changes? These two population distributions are graphed on the same line at the bottom. Their means are both 0. Okay, both of them. Maybe I should do that in purple, since that's the combination of the two. Ooh, purple might be a little hard to find. Okay, there's the purple mean at m equals 0. But look at the difference in the standard deviations. This standard deviation is 1, so it's 1 between there. This distribution has a standard deviation of 2. So actually, I think they should have changed the way these are marked. This is the standard deviation for the red graph. And this is the standard deviation. One standard deviation above and below the mean for the blue graph. So the standard deviation is 2 for blue. There's the 2. And the standard deviation is 1 for the red distribution. See the difference there now? Okay, the mean's the same, so one of them's just skinnier than the other and the other's fatter. You can see this difference when you have two populations or two samples graphed on the same scale for the curves. Usually they are not seen on the same scale. So as long as we change the scale for each of them, we can just use a standard curve. And by the way, I uploaded a whole sheet of curves, so you won't have to draw these and get, kind of sloppy ones like I have there. Okay? You'll find a whole sheet of those that you can use to do your homework. Just print it out and write on it. Okay, let's move on. Oh, I left a few artifacts behind, didn't I? Let's get rid of those. Okay, just a reminder now about the empirical rule. Okay, 68% of the data is between 1 and 2 standard deviations above and below the mean. So that's minus 1 standard deviation. plus 1 standard deviation, plus 2 standard deviations, etc., to positive 3 and negative 3. Or you can use the empirical rule wrap to remind yourself of these values. Remember this last one out here? Do not forget it. It's 0.15%. 15 hundredths of a percent, but it is still there. Moving on. Oh, by the way, let me set this in here. Okay. Previously we talked about outliers being the mean plus or minus 3 standard deviations either side. Now we're going to pull that in a little bit. Another common way of looking at outliers when you're talking about standard deviations and means is that the outliers are beyond 2 standard deviations above or below the mean. That is totally a choice of the statistician. There are other ways we're going to be analyzing whether something is normal, whether something is an outlier, whether a distribution is normal, and whether the sample or population with which we're dealing has outliers. Okay, we'll make that distinction later. The area under the curve represents either the proportion of the population with the characteristic described by the interval. Notice that when I draw my normal distribution, flatter or shorter and wider, my standard deviations have to spread out also. It's just the way I've drawn it. Okay, so let's say this is a distribution of the hatching times. For blue hens, chickens, and yeah, that is a breed. Eggs. It's probably blue hen chickens, eggs. The actual results of recording the hatching times for blue hen chicken eggs would be a histogram, but they are approximately normally distributed, so I'm going to talk about it as if it were a normal curve, and we can use this as a probability density function. So let's say for some reason we are interested in knowing how many of the chickens hatch before 490 hours. That's 490 hours have elapsed. Okay, how many of the eggs hatch? So before that time, so we want an x less than or equal to 490. And this area under the curve would represent the proportion of the population with the characteristic described. Okay, the proportion of the population of eggs that hatch sooner than or equal to 490 hours. Let me make a little bit of room here. Okay, because there is another thing it could represent. It could represent the probability that a randomly selected individual will have the characteristics described by the interval of values. In other words, if you have a whole bunch of blue hen chickens' eggs, if you randomly select one, this area represents the probability that it will hatch in less than 490 hours. Okay, let's move this out of the way. Clear up the rest of it. All right, let's talk about refrigerators. Okay. The lives of refrigerators are normally distributed. That means you could represent their lives with a normal distribution. It's a little bit lopsided, but we're going to go with it for now. Okay, so there's the normal distribution. The mean is 14 years. Notice I'm using population symbols. And a standard deviation of 2.5 years. So the first thing you're asked to do in this problem, so this is an example of how we would do your homework. Okay, for part A, you're to draw a normal curve with the parameters labeled. So I don't want you to just come in and write mu and s plus 2s. No, I actually want to know what those are. So, in other words, the mean here is 14, and these are all years. And let's call this refrigerator lifespan. You could call it useful life or whatever. Okay, 14 years. 2.5 years above the mean, one standard deviation above the mean would be 16.5. Then we'd have, what, 19, and then 21.5. Below the mean, we would have 11.5, 9, and 6.5. So I have drawn a normal curve with the parameters labeled. Part B asks me to shade the region that is represented by the proportion of refrigerators that last more than 17 years. So if I come in here, 17 years is about there, and I want to shade the proportion that lasts for more than 17 years. So there it is. And I'm told that the area under the curve there is 0.1151. We'll talk about how to find that later. But right now I'm told that is the area. I have that information. So how could I interpret that? There are two ways. One is as a proportion. Okay? So this is a decimal, first of all. I need to convert it to a percentage. That's 11.51%. 11.5 I think will do for our present purposes. So I would say that that 11.5% of refrigerators last more than 17 years. Or I could say that the probability of randomly choosing a refrigerator and having it last 17 years or more is 11.5%. So let me type those out formally for you. Okay, we need to make a little room here. Let's shrink this a bit. We expect that 11.5% of refrigerators last more than 17 years. Let's correct that. All right. Another way to say that, or we could say there is an 11.5% probability that a randomly selected refrigerator will last more than 17 years. All right, I'm going to attempt to publish this and get it uploaded, so hopefully at least some of you will be able to view it before class. It may take me a while, but wish me luck.